Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one's entitled Astronomical Quantum Mechanics, Gravitational Potential, and Orbitals. Now, in Article 555 entitled Planet X and Why Physics Has Failed, I talked about how the Planet X observations have led to the understanding that all energy and matter comes from light, and how everything from atoms to stars and galaxies work according to the same patterns and laws. Thus, since stars operate like atoms, they may thus be called superatoms. And since atoms have energy levels, we would expect energy levels to also manifest at the astronomical level. In other words, we would expect stars and planets to also have energy levels. They should have energy levels on the inside so that energy decreases from the core to the top of the atmosphere for all neutral atoms and ions, positive ions or even negative ions, making up each of the layers. Free electrons, since they are negatively charged, have increasing energy and the further you get from the core. But for neutral atoms and ions, we have increasing gravitational potential and gravitational energy as we move towards the core. And this is illustrated here. This is the core of a planet. This is the liquid layer. This is the solid layer. As we move away from the center, the gravitational energy in the matter making up these layers will decrease, and it will be in energy levels. The lowest energy level that makes up is part of the object will be the atmosphere. And that's where we also find the electron, most of the free electrons, which then have also the greatest gravitational potential energy of all the electrons making up this celestial object. Now, if a celestial object orbits another, it should orbit at a distance which is associated to its gravitational potential. Thus, celestial objects should have external energy levels as well as internal ones. Therefore, planets orbiting the Sun should be in an orbit which is associated to its gravitational energy. This is how it can be seen that Jupiter is an acquired object, i.e. a Planet X object re-energized by the Sun, but still having a very large but yet dead core, which therefore is very low in gravitational potential. And this is illustrated with this diagram. Planets orbiting further out from the Sun have to have a lower gravitational potential. But larger objects should have larger cores, and larger cores, if living, should have greater gravitational potential. This means that Jupiter, the largest solar system planet, there's Jupiter there, cannot be a living planet. It must have a dead core, and is thus a Planet X system object, which became a solar system object. The same applies to all the gas giants, and you may look at Article 523 entitled Planet X and the Solar System. Jupiter and all gas giants are recent acquisitions. In other words, these are Planet X systems, stellar cores that came to the Sun possibly thousands of years ago and were re-energized by absorbing matter from the Sun and then turned into solar system objects. But their cores remain dead. Their cores are still very low in gravitational energy, which is why they seem to be of a much lesser density than they actually are. They have a very large, very dense core, but it's low in gravitational energy. But if all the planets in the solar system orbit in different energy levels, and then we should be able to obtain an equation for gravitational potential which is quantized. A quantized equation is one in which variables change in steps rather than continuously. So using known orbital parameters for solar system objects, I'm going to derive quantized equations which describe the Sun's gravitational energy levels. I'm going to use the relationship between the Sun's rotational period and the planet's orbital periods to come up with the required quantized equations. And I would like to thank the subscriber who left a comment under one of my videos informing me of this relationship. Now, the sun's orbital period is not actually an easy thing to determine as it changes for different solar latitudes. It is about 24 days at the equator, but as fast as 36 days at the poles. However, the movement of sunspots can be used to determine the sun's average rotational period, which turns out to be between 27 and 28 days. And I'm going to use 28 days as it is likely that the core moves a little faster than the outer layers of the sun, and because it divides exactly into Venus's and Earth's orbital periods. So in this table, I have all the several planets: Mercury, Venus, Earth, Mars, Jupiter, and Pluto. I have their orbital periods, that's Tn, and here I have divided the orbital periods by the sun's rotational period, which I've said to be 28 days. So this is the number n. It's Tn, the orbital period. So 88 divided by 28 is 3.14. Venus's orbital period is 224.7 days. Divided by 28 days is 8.02, almost exactly 8. And Earth's is 365.2, it's 13.0. That's a whole number there. And that's exactly what we're looking for. But Mars, 687 divided by 28 is 24.5. It's only half a whole number, which suggests that the energy level quantum number is actually twice this number. So that would mean that Mars' energy level is actually 49. But I'm going to use this n here because it simplifies the equation. There I just give the semi-major axis. And as you can see, Earth is of course 1 because 1 astronomical unit is the distance between the Earth and the Sun. So Mercury's period does not fit the scheme as well as Earth's and Venus's. It's 3.14. And then I just set it to be 3. But Mercury seems to be a newly created planet, and it is thus likely that it has not yet completely settled into a stable orbit, which may be why it has such a large eccentricity or elliptical orbit. And you may look at Article 524 entitled Mercury Created by the Sun Due to Planet X. Jupiter and all the gas giant planets as new acquisitions are also not likely to have yet settled into their perfect stable orbits, so we can expect their orbital numbers to differ somewhat from whole numbers. Pluto, like Mercury, has a highly elliptical orbit and is therefore likely to have been recently created by the Sun as well. So according to the above scheme, Mercury is in the Sun's 6th energy level. Venus is in the 16th and Earth is in the 26th energy level. But I'm going to keep on using n, the orbital quantum number. That's what I called it here, orbital quantum number. And that means that Earth's quantum number is 13 and Mars is 25. And that makes the calculation simpler. So we'll start with the fact that the orbital period of each of the planets, which I call Tn, is now given by n, the orbital quantum number, times the rotational period of the Sun, T Sun. Then from Kepler's third law, we have this equation. T squared is 4 pi squared over GMA cubed. And if we substitute equation 1 into there, we get n T Sun there, all squared. And from that, we can solve for an cubed, which is the semi-major axis, which is the average distance each planet has from the Sun. And so I just reversed the equation. So now an cubed is the subject. Then I want to obtain an equation for potential. And for potential, I'm going to use gravitational potential energy per unit mass. So I'm going to take the gravitational potential energy equation, or something looking somewhat like it, and just divide it by mass. So we just end up with gm and an m divided by the distance from the sun for each planet, which is an, the semi-major axis. Now, the gravitational potential energy equation has a negative sign in it. I'm not going to use that. I'm just going to set it to be positive, because the core of planets have positive gravitational energy. Now, so I'm just going to use Vn equals Gm over An. That means that Gm is Vn times An, and then I'll substitute that into the equation here. So that's equation 3 for An cubed, and I just substitute for Gm. So now Gn is Vn An or An Vn. Then one of the An's cancels, so this becomes An squared, that disappears. And then we have Vn over 4 pi squared, n squared, t sun squared. And I want to solve for Vn. So Vn will become the subject of the equation. The 4 pi squared will go there. The An canceling there. We have An squared. And then we end up with n squared and t sun squared in the denominator. So we obtain this equation. So this is now a quantized equation for gravitational potential, and thus gives the gravitational potential for each of the sun's energy levels. The next step is to obtain a quantized equation for the orbital position. And using the known values for g, which is 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared, and the sun's mass, m, which is 2 times 10 to the 30 kilograms, we can find the first orbital radius by letting n equals 1 in equation 3. So let's go back to equation 3. Here it is. So we're going to let n equals 1. So that's 1. So we just need Gm divided by 4 pi squared times the sun's rotational period. And so this is what we do here. So A1, that's a 1 there. And what we obtain, if we substitute all the values, we obtain 27 times 10 to the 6 kilometers, so 27 million kilometers. We can write that in terms of the sun's radius, which is 695,508 kilometers, or we can write it in terms of astronomical unit. It's 0.18 AU. It doesn't matter. We can choose whichever one works the best, or gives us the simplest kind of scheme. So we now then have that the orbital distance for each planet, the average orbital distance, or the semi-major axis cubed, and this is from that equation, there is now simply n squared times A1 cubed. So the orbital radius for the first orbital for the sun. So that means that we can take the square root on both sides, and we get n to the 2 over 3 A1. So from there, we now have basically an equation, and n will change from 1, 2, 3, and so on. And from that, we can use that to obtain all the orbital radii of all the planets, and actually all the energy levels that the sun has. So to check that this formula is correct, we're going to calculate the Earth's orbital radius. And Earth, remember, had an orbital quantum number of 13. So the Earth's orbital radius would be A13. So we have, instead of n, we write 13 to the 2 over 3 times 0.18 AU. We use that value for A1. And if we multiply that out, we get 1 AU. And we can do the same thing with the formula where we had it cubed. And we then have 13 squared times 0.18 cubed, and that gives us 1 as well. So it is correct, because the Earth is at 1 astronomical unit from the sun. Now, substituting equation 7, which is given here, into equation 5, And that's the equation we had for the gravitational potential, the quantized equation for it. We're going to obtain something simpler. And so if we substitute that into there, so now let's go back there. AN squared is what we need, which is given by this equation there. And so this is n to the 4/3 times a1 squared, and then n squared into n to the 4/3. So that's n squared minus 4/3, n to the 2 minus 4/3, which gives us n to the 2/3. And then we'd have the t sun squared times a1, which we know what it is. It's given by that value there. So now we have all the gravitational potential associated with each orbital in terms of the first orbital in the scheme. And we can calculate then what the first gravitational potential, so the sun's first orbital would have this gravitational potential. And I calculated that using the value for A1 of 27 million kilometers. And then T sun is 28 days, and I then changed units to seconds. And so this is how you change. So 28 days, 1 day is 24 hours, and 1 hour is 3,600 seconds. So I have 28 times 24 times 3,600 in there, and then squared. And then multiply by that squared gives me 4,917 kilometers squared per second squared. That is the unit for gravitational potential. And in that unit is the number that I think makes the most, you get the number that makes the most sense in these units. And then all other gravitational potentials can now be written in terms of the gravitational potential associated with the sun's first orbital, which is given by that value. So then what we would get is just Vn is 1 over n to the 2/3 times V1. And then we can obtain the gravitational potential for all the planets using the scheme. So for Earth, n is 13, so we just have 1 over 13 to the power of 2/3. And that's 0.67 times V1, 4917. That gives us 882 kilometers squared per second squared. Then for Mercury, Mercury is closer to the sun, so we would expect a larger value. And we have a 3 to the 2/3 instead there. And we get 2355 kilometers squared per second squared. And for Jupiter, n for Jupiter is 155. So if we use that, we get 168 kilometers squared per second squared. Hence, the gravitational potential drops with increasing distance from the sun as expected. So in conclusion, stars, just like atoms, have energy levels, and thus using a relationship between the sun's rotational period and the planet's orbital period, quantized equations for the gravitational potential and the orbital radii of the planets have been obtained, as well as a scheme for determining the gravitational potential associated with each energy level. And here are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.